In January 2020, a team at OpenAI published a paper called Scaling Laws for Neural Language Models. Jared Kaplan, first author, and they showed something that changed how the entire industry thinks about progress. If you plot model size against loss on a log-log scale, you get a straight line, not a curve that plateaus, not a curve that saturates, a straight line for 7 orders of magnitude, which means if you want a better model, you can just make it bigger. That's the whole hypothesis. Last video, BERT and GPT, 2 ways to train a transformer. GPT-style causal LMs kept scaling. This video answers why bigger models kept getting better, what the scaling laws actually say, and where things fall apart. Because they do fall apart. Chinchilla 2022 said everyone was doing it wrong. 7 established the fork. BERT-style encoder for classification. GPT-style decoder for generation. The GPT branch had one thing going for it that BERT didn't. It kept getting better as you made it bigger. GPT-1 wrote nonsense. GPT-2 wrote paragraphs. GPT-3 wrote essays. Same recipe, more parameters, more data, more compute. And this raised an obvious question. How much better does it get, and can we predict it? Today's puzzle. If neural networks are theoretically capable of many things, why does one specific recipe, bigger transformer, more text, more compute, keep working? Answer: because there is a mathematical regularity underneath. It's called a scaling law. And once people published the equation, the whole field started training bigger models on purpose to hit it. Today's 3 beats. First, Kaplan et al. 2020, the original scaling laws paper. What it measured, what the straight lines mean, and what people got out of them. Second, Chinchilla 2022, Hoffman et al. At DeepMind. The paper that told everyone they'd been training oversized models on undersized datasets. Compute optimal. Third, emergent abilities. Why some capabilities appear suddenly at scale instead of smoothly, and why the field genuinely disagrees about what any of this means. Beat 1. Kaplan et al. 2020. The team trained a bunch of GPT-style models, all different sizes, from a few million parameters up to over a billion, on different amounts of data with different amounts of compute, then plotted test loss against each of those 3 variables: parameters n, dataset size d, and compute c. And the shocking result, each of those plots was a straight line on a log-log scale. The equation that fits the plot is simple. Loss equals some constant divided by parameters, raised to a small negative power, about -0.09. Same shape for data, same shape for compute. Which means, if you double the parameters, you can predict exactly how much the loss will drop. If you spend 10 times the compute, you can predict the loss too. And the field went, oh, we can PLAN this, we can budget it. The paper's practical claim was even more specific. Given a fixed compute budget, say 10,000 GPU hours, you should spend most of it making the model bigger, and only some of it on more data. So OpenAI trained GPT-3, 175 billion parameters, on 300 billion tokens. Following the Kaplan recipe, it worked, it defined the field, and it was, as it turns out, wrong. Almost exactly wrong. Beat 2. Chinchilla, March 2022. Jordan Hoffman and team at DeepMind, arXiv 2203.15556. They redid Kaplan's experiment with more care, and discovered Kaplan had trained his big models on too little data. So the loss curves he saw understated how much data mattered. When you actually give the models enough data, params and tokens should scale about 1:1, not the Kaplan 90-10 split. To prove it, DeepMind trained Chinchilla, 70 billion parameters, but on 1.4 trillion tokens, about 4 times more data than GPT-3. Same compute budget as GPT-3's 175 billion. Chinchilla beat GPT-3 on almost every benchmark. Smaller model, more data, better results. That result rewrote the training recipe for every major lab overnight. Llama 2, Llama 3 Mistral, DeepSeek, every recent open model is Chinchilla scaled or beyond. The Chinchilla story is instructive for another reason. Even the paper that corrected the scaling law was still fundamentally a scaling law paper. Nobody in 2022 said we need a smarter algorithm. They said we need to allocate our compute better. The hypothesis is still the same. Scale is the story. The Chinchilla fight was about how to spend the money, not whether the money buys progress. Beat 3. Emergent abilities. Wei et al., 2022. Google Research. arXiv 2206.07682. They noticed something weirder than the smooth loss curves. On some benchmarks, arithmetic, multi-step reasoning, chain of thought, small models performed at random chance level. Then at a certain scale, around 10 billion parameters, the model suddenly went from 0% to 60 or 70%. Not smooth, not a straight line, a phase change. This is the piece the field genuinely doesn't agree about. Some people, including Wei, see this as real, novel, and important. Bigger models learn new kinds of things, not just better versions of old things. Others argue the emergence is an artifact of how we score the benchmarks, change from exact match to a partial credit metric, and the smooth loss curve returns. That's the Schaefer 2023 argument. Where does that leave us? In 2026, every frontier lab still bets on scale. Data is the new bottleneck. We're running out of clean text on the internet. Compute is the new price of admission. You cannot enter this game with under $100 million. And the scaling hypothesis has quietly become the working theory of the entire field. Maybe understanding was always just scale. That's the puzzle we're setting up for the rest of the course. 3 takeaways before the quiz. 1. Kaplan et al. 2020 showed test loss follows a power law in parameters, data, and compute. Straight lines on log-log plots. 7 orders of magnitude. That's the scaling hypothesis. 2. Chinchilla 2022 corrected the recipe. Params and tokens should scale about 1-to-1. GPT-3 was undertrained on data. Chinchilla beat it with less than half the parameters. 3. Emergent abilities. Some benchmarks show a sudden jump at a threshold scale. Whether that's real or a metric artifact is an open question. Scale is still the working recipe. Quiz 1. What did Kaplan et al. 2020 discover about neural language model loss? A. It plateaus once models get big enough. B. It follows a power law in parameters, data, and compute. A straight line on log-log plots across many orders of magnitude. C. It goes up as you add more parameters due to overfitting. Or D. It depends entirely on the choice of tokenizer. B. arXiv 2001.08361. Straight lines on log-log for 7 orders of magnitude. That single result gave every lab a formula to plan training runs against. Doubling parameters gives a predictable drop in loss. That is why the money flowed. Quiz 2. What did the Chinchilla paper Hoffman et al. 2022 show? A neural networks are unpredictable and cannot be planned. B parameters and training tokens should scale roughly 1-to-1. GPT-3 was undertrained on data, and a smaller model with more data beats it. C bigger models are always worse than small ones. Or D attention doesn't matter, only depth does. B. arXiv 2203.15556. Chinchilla was 70B params trained on 1.4 T tokens. It beat GPT-3's 175B on almost every benchmark, using roughly the same compute. Every recent open model, Llama, Mistral, DeepSeek, follows this recipe. Quiz 3. What is meant by emergent abilities in large language models? A. The model becomes conscious. B. Some benchmarks, arithmetic, chain of thought, jump from near random to strong performance at a threshold model size, rather than improving smoothly. C. The model starts speaking a new language. Or D. The GPU learns to program itself. B. Wei et al. 2022, arXiv 2206.07682. Whether this is a real phase change or a scoring artifact from exact match metrics is genuinely disputed. Schaefer et al. 2023 argue it's a mirage. Either way, The observation drove every lab to scale further. Back to the puzzle. Why did one recipe, bigger transformer, more text, more compute, keep working? Because there's a mathematical regularity underneath. Loss scales predictably with 3 variables. Scale was the story. Whether it's the whole story is what the field is still arguing about. Next video, we look inside GPT and see what actually goes into the model. Not English, tokens. Next time, tokenization inside an LLM. We covered BPE way back in lecture 3. Now we look at it running live inside GPT. The English never enters the network. What does enter? And why one word is not one token? And why strawberries has 3 R's but GPT can barely count them? Hit subscribe.